Okay, welcome to everybody to this webinar on tuning waste into value. This webinar is part of a series held by ASIP, which is on modeling and simulation in biotechnology and biochemical engineering. Of course, biomodeling is always part of this type of processes if you develop such things. It can be on a metabolic level, it can be on modeling the cells, it can be on modeling of parts of the process, of course. So we will have two very attractive, interesting presentations given by Michael Sauer and Michael Egermeier. Both of them were for a long time also at Boku University, also involved within ASIP. So many of you may know them, and they are in close connection to our university and also to ASIP. So what is the topic about today? Of course, circular economy is something that is very, very attractive and important. It is a topic that is there for already quite a while. And the motivation is always somehow to make use of waste products, of side streams from agriculture, and to convert this into valuable feedstocks and, for instance, fuels, chemicals, and materials. Our webinar is organized that way. One perspective is very, very strongly related to industry view because Michael Sauer is at OMV and he will provide us some insight into the concepts that are there to make use of biotech processes to also contribute to this field of circular bioeconomy. And I think what we will do first, it's 20 minutes presentation. After the presentation, there will be 10 minutes for questions from your side. Then we will have the second presentation, and afterwards, we will have a breakout session where we can continue with discussion whenever there is need for that. So I would like to start with the first presenter. So Michael Sauer, please give us some insight into OMV's approach to circular bioeconomy.
So the microphone trap, can you hear me now?
Yeah.
Very good. So it's a great pleasure for me being here in this double feature of Michael's. And actually, our presentations belong quite together. So Michael is not only a friend of mine, but also a collaboration partner. And we were thinking a little bit of how to structure this afternoon. And in this case, I will focus particularly on the resource side of bioresources, which are not waste, but we want to create value from them. And I think Michael is more focusing on the technology side so that we really can a little bit look at the entire value chain. Having said that, I also have to say that I have to look at the resources, and I want to give you a little bit a flavor of how complicated it is to move in that direction, particularly when you are working in a large company. So I think I don't need to introduce OMV in much detail to you. So we are essentially right now a classical fossil fuels company, so a global energy and chemicals group. But importantly, we want to become a leading integrated sustainable chemicals, fuels, and energy company. And of particularly importance is that we want to become climate neutral by 2050. Having said that, and considering that we are one of the largest industrial companies in Austria, so you see here some numbers like 20,000 employees, you can understand what the challenges are to, let's say, turn this big ship from one direction, namely using and valorizing fossil resources, into something else, but at the same time being a reliable partner. So our purpose in this is reinventing essentials for sustainable living. And here I want to focus very briefly onto the word essentials, because that is really important for us when we think about the current situation. So while on the one hand, we are of course very dedicated in becoming, let's say, green and sustainable, in becoming a company that provides all of the things that we are providing now, but in a carbon neutral way, we must make sure that the energy security of Austria is safe. So you know that energy security depends on this company. So the option to simply just stop using fossil fuels at this moment is not there. We have to be as a reliable partner. And to give you a little bit a context of what that means is, so we have three business segments, and our chemicals segment, for example, provides about 7 million tons of base chemicals, and this goes particularly in the polyolefin production. And you might have heard from the news that our daughter Borealis just now fused with Borouge International and Nova Chemicals to form the fourth largest polyolefin producer of the world. So this is an important stream of products coming out of our company. And we're talking about 7 million tons. And then we have fuels and feedstock, which is composed of the refineries. We have three refineries. And here I calculated it, so in the refining world, it's typically 307 of these kilo blue barrels per day, which in the end is 18 million tons of petroleum, which we are refining, and the same amount again in energy for gas. So we are talking about millions and millions of tons, and that is exactly the challenge that we have to address. And so what we want to do is, of course, to use sustainable materials. And this is why now we are really working on making sure that we are not producing any waste as societies anymore, but this, what is not waste, is actually value. And here we have the typical things, so I think there's nothing new for you, but plastic waste is one of the things we are looking at, but also carbon dioxide and, for example, used cooking oil and agricultural side streams. And again, this is all more or less to give you a flavor of what we are doing and a flavor also of the difficulties which we are facing. So talking about plastics, plastics are very important materials for our societal development. And here you can see some numbers. So we are producing currently about between 400 and 500 million tons of plastic per year. And so this is definitely something which we will also need in future, but you see here what happens in the end. So half of it, for example, is still landfilled, and that is really something that we can improve on. And one of our, let's say, proprietary technologies which we developed, I'm well aware that I'm talking to a biotechnology audience, but bear with me. I want to tell you that while biotechnology is really important, there are other technologies. And what we need to become sustainable in future is really a mix of very different approaches to use very different carbon sources. And one of our proprietary technologies is the so-called re-oil technology, and this is a technology addressing polyolefins. So polyolefins are, I already mentioned it, one of our major chemical products, and they are very important and also here produced in the millions of tons per year. And here you see, for example, something that makes the refining industry quite difficult in future. Because if you look at the white line, that's the global oil demand, that is more or less, it's increasing a little bit, but not extremely. But if you look at the blue line, it's increasing very much. So essentially, the gap between the petroleum we are actually using and the polyolefins which we are producing is getting higher. Why is this a problem, or why is this something that we have to address? If you look at the refinery, how it works now, of course, you put petroleum in, and then you get a mix of products out, which could be aviation fuel, which could be gasoline, petroleum, or whatever, and the base chemicals for olefins. But you cannot produce one without the other. So if you produce less gasoline and less aviation fuels, you cannot produce more polyolefins at the same time. So here are gaps which we really have to fill with technology. In very short, the ReOil process is a pyrolysis process, so that means the plastic is fed into the system and in the end is turned into something that pretty much resembles petroleum from the beginning. So we get heavy oil, light oil that we can directly feed into the refinery. And this is why we say it's closing circles. You start from petroleum, you make polyolefins, you go through the ReOil process, and you end with petroleum that then you can use again to produce fuels or polyolefins or whatever you desire. And where are we technologically? So we have a plant running now that is able to produce about 2 tons of polyolefins per hour. And with this, we are gathering the data to scale that up to real industrial level. And we want, after 2030, to have an industrial plant in Schwechat that is able to produce to use 25 tons of polyolefins per hour. So you see that is really a technology that is ready for the market, and that is something that can be done. So why and what is it with plastics now? Polyolefins are material of the future, and here's also something I want to draw your attention to on the right side, what you can see. So this is a high voltage cable. So if you think about that, we are really wanting to electrify all of our societies. That means we need a lot of cables to build up our grids. And the only really useful insulation material which we right away have are polyolefins, particularly the low density ones. So what you see here is a growing market for exactly that plastic, and that we need it, we can bury it, it's buried for decades, and then you can reuse it. But on the other hand, on the right side, what you can see is there's also a problem, because using these longevity materials for something like daily use for packaging, what we are currently doing, is not a good idea, because we have many other problems apart of the CO2 and fossil origin. For example, what happens when these materials come into nature. So here we really need to do something and to develop new products which actually solve also those environmental problems on top of the fossil origin. And this brings me to exactly what we are doing. So in order to transform our company, we innovate. So we are developing for OMV new renewable resources that we can actually tap to get carbon into our company. We want to replace traditional fossil-based products with sustainable products, but, and this is important, we also want to develop new products for adjacent makers. So for example, instead of polyolefins, we could be producing other plastics which are less environmental detrimental. But again, to give you a flavor of the complex network we are working in, I want to draw your attention in this case to oil, to sustainable aviation fuels and this context. So one of the things is that when we want to produce aviation fuels or other fuels from secondary carbon sources which are not fossil, then we are moving in a world that gets extremely complex. And I want to draw your attention to the middle scheme. So what you can see here, excuse me, is how the European Union currently treats this stuff. And what you see is that, for example, when you think about car transport, if you think about gasoline and you want to use crop-based ethanol, for example, this is allowed, but it's capped. So you cannot, for example, substitute the entire gasoline with ethanol from crop. In aviation fuel, that's totally forbidden. But if we think about waste, the same thing. It is capped for gasoline, but you could use it, for example, for aviation fuel. And this tells you already something, some of the challenges that a company like us faces. So we have this intake of millions of tons of petroleum, and we have to substitute it with other carbon sources. But these carbon sources must be a mix from very different origins, and we cannot use all of these origins for all of our uses. That means we need to balance this, and we need to figure out, let's say, like a matrix of what can we use what for. If we look at international, and we are an international company, then it gets even more complex. If you think, for example, here, Malaysia, Indonesia, Southeast Asia, their biofuel industry obviously depends totally on palm oil, which is something that is completely banned in Europe. And here, to make also just a point about it, I told you already that OMV alone is using about 35 million tons of fossil resources. And here you can see that that's more or less corresponds to the market of what is currently used in oils worldwide. And in Europe, for example, it's mainly rapeseed oil, while in Latin America, it's mainly soybean oil, and all of that satisfied just a tiny fraction of the market. So we have to do a lot to go on here. Also, what we can see is that the increase of feedstock availability, so which kind of oils are available when, is growing with about 1.4%, while the demand for that is growing with way over 4%. So we have a disparity between demand and supply. Again, that points into one direction. We have to be innovative to solve those problems. And then, and this brings me now a little bit closer already to biotechnology. Interestingly, if you really look at the transformation of plant oils or used cooking oils or something like this into sustainable aviation fuel, what are the major costs? And 80% of those costs are actually the feedstock. So all the processing to come from your oil in which you fried your schnitzel in to the airplane fuel tank, that costs only about 20%. 80% is still the price of the feedstock. Why? Because quality counts. You can imagine if you fried your schnitzel, it's a dirty oil, so you have to clean it, you have to store it, you have all the logistics, because there are many people frying schnitzels in Austria, and you have to collect all of this. And that increases the costs, and that makes it much more complicated than something like petroleum that you can just get with a big ship. So, what concretely would biotechnology do in all of this? Yeah, so this is no magic. So I'm not telling you a lot of very new things here, but very classically, we definitely think about biomass. We definitely think about agricultural side streams, which we have to transform into useful substrates, and then we process them either enzymatically or microbially, and then we have to purify them to get to our products. So pretty classical industrial microbiology. But in the context of a refinery, the point is very clearly and very easily you come to scales which are very unheard of when you compare it to most other biotech processes which are currently running on the market. And one thing we are interested is, for example, different kinds of straw. Having said that, I can also directly say in Austria, straw is not really available. We have hardly anything. But we have to look outside of Austria. We have to look into other regions to get into straw resources which are useful of us. And then, like for the cooking oil, you immediately come into logistic problems, because if, for example, farmers somewhere in a remote country have the straw on their fields, that is not something that you can use easily. But let's say we have to tackle those logistical problems, and we do this, then one of the things that are important, in my opinion, is that value generation, straw or agricultural side stream to chemical or fuel alone is not sufficient. You will never ever be able to make, for example, simple secondary ethanol that you just take straw, you make ethanol, and everything else is lost. This cannot be competitive in prices to petroleum. You need to create a refinery that is a system bringing different products and different value streams. And some of the value streams I mentioned here, for example, if you have a microbial process, you have biomass which you can use. You have to make use and value out of it. You have biogenic CO2, which gets more and more valuable nowadays. We have our fuels. but we have also lignin, and we might have minerals from the ashes. And each of these need to create value, and only then I will be able to produce fuels at the price from a renewable resource that makes industrially sense. So essentially also such a concept involves a platform, because also here a big rethinking is necessary. So talking to colleagues, let's say in the refinery, they are used to a big tube of petroleum coming into the refinery. It's one feedstock. And from this feedstock, all of the products which we are selling are produced. But in future, that's not possible, because if you think about these millions and millions and millions of tons, nothing exists that could simply substitute that. So what we have to do is to take different feedstocks, transform them into a common platform molecule, which could be sugars, most probably it's not. It could be ethanol, it could be methanol, it could be butanol, whatever that platform is. And from there to develop the refining, let's say, network that produces the different products that we want to market in the end. Yes, and then what are we doing? So, for example, one of the things that, of course, the current refinery is doing, there are a lot of catalytic processes running, which have been developed like since decades, and they are extremely efficient. But usually these catalytic processes are using very high temperatures, high pressures. Actually, refining in the current sense is a very hazardous industry. And in order to change that, as biotechnologists, clearly, we can use enzymes. So we want to substitute some of the catalysts which we are using currently with enzymatic reactions. And I think you know why, that we use less energy for that and that it goes at benign temperatures. And the last thing I want to make, the last point, is purification of the products is usually the thing that biotechnologists are very bored about. So at least I have been a lot of time. I'm the microbiologist, very fond of developing processes, but to purify the product, that's the thing that is boring. However, that's the thing that makes most bioprocesses fail, because that is very expensive, and a lot of processes never reach the market because the purification is not developed. And here OMV has a big advantage, because our core business is refining and purification. So we can use a lot of our existing processes and a lot of our existing knowledge in the company and combine it with biotechnology. And this is why I think that there is a bright future of biotechnology within also a refinery like OMV. And this is what we do to transform, we innovate. And with this, I'm very happy to take questions if there are.
So thank you for this very interesting presentation. It's nice to have this view from your side, because it's quite different from that what we are usually busy with. So all this work that is around how to get the feedstock and so on. So are there questions from the audience? If not, I will simply start with the question, because what you told us, there is this product polyolefin plastics, and that there is this increasing demand to be expected in the future. And so in your position as a company producing the basic material, but also being active in doing the recycling, what is your opinion on that? Is there a way simply to make it possible that that this material is used for long-term application, not only for simple packaging and this type of things? So I think this is closely related to that, what the company producing the material is having in mind.
Yes, but the point is, I think it is definitely possible to separate those things from each other. So to use the right material for the right application. But there are two, let's say, prerequisites that we need. One is we have to have useful alternative materials. So we have to have plastics or whatever it is which are cheap enough to compete and which are useful enough that the customer has the experience the customer wants to have. And secondary, we need to have the regulations in place that kind of also force the market to do the right thing. So if I think about Italy, where they banned these plastic bags and now they have these starch-based bags, which I'm not a very friend of, because I think in this case the material does not really hold up to the need, but in principle these things work. And here I think particularly material scientists would be called for. Let's develop together materials which are useful in such contexts.
Okay, thank you. And what is about the costs? If you compare now this recycling concept and compare the costs for the product in the end to that what you have for the virgin polyolefin from oil?
Well, currently the costs are higher. That's not a question, but I think that is due to different factors. One factor is scale, because we are in a too small scale, so we need to scale it up, and that makes it cheaper. And the other thing is there is still some innovation needed in terms of feedstock cleaning, because this process really needs a fairly clean polyolefin stream. And the question is, where do you get that from, and how expensive is it to clean, let's say, the polyolefin stream which you have from all the materials which shouldn't be inside? So that actually, at this moment, eats a lot of the costs away.
Okay.
But innovation is ongoing. Yes?
There is a question in the audience, in the chat from Antonia Zerubin. She was asking, as you mentioned, logistical barriers when it comes to agricultural waste, example, soil health. Are you tackling these constraints? If yes, do you know how?
Yes, we know, and we are tackling that, because the logistics is the starting of everything, and that is also a really decisive cost factor which you have, because you have to get your material. So what preferably we do is to work really with the farmers or with consortia of farmers that have these things in place. So first of all, you might not be able to take all the agricultural side streams, because partially they must remain on the field for soil health. You're totally right about that. We are taking care about that, not in the sense that we know what to do, but we trust the farmers know what to do. And then what we really like is to have consortia of farmers that are working together and that are establishing the logistics, so that we have just points in which we can get the material. And also to give long-term stability, on the one hand to us, because we need also to have a certain security that we can get that feedstock also 10 years from now. But on the other hand, that's value creation for the farmers, because they also want to know, if they now, let's say, establish a logistical network, that makes sense also 10 years from now. But that's a tricky thing, and that is not easy.
So I cannot see any raised hand in the audience. So then another question from my side. There is this competition between this organic material used for whatever recycling or for the purpose you mentioned here. On the other side, there is agriculture, there is food production, so you are somehow in a competition, and there is for sure limited volume available for replacing the energy or the material that comes from petrochemistry. What is your opinion on CO2? Because this would, as a carbon source, this would not interfere with any agricultural use. Because there are also
Yes,
these ideas on converting this into biomass and then using this material.
yes. So there my answer is twofold. So first of all, yes, we need CO2. So that's not even a question. So you're totally right. The numbers do not match. Agricultural waste will never ever be able to substitute what we are using in fossil fuels now. So we need other sources, and in my opinion, the only other source we have is CO2. The question is, where does this CO2 come from and how expensive it is to get? That's a question that needs to be addressed. But there are technologies, partially biotechnology, but here I would personally count much more on also the electrochemical conversion of, for example, CO2 in methanol or something that can be used then for whatever you want. That is an absolute prerequisite. But that, and this brings me to the second part of my answer, if you ask me as biotechnologist what I'm really envisioning for the fuel use, and we have some fuels which we cannot substitute. For example, aviation at this moment has no alternative to carbon-based fuels. So we can have electrical cars, we can change a lot of things, but we cannot change airplanes for technical reasons now. And here, for example, this electrolysis and coming from CO2 to something makes totally sense, and this matches the numbers. But biomass is still a resource which is there, and this has larger molecules already. And so this is why I would envision to use the biomass for material production and not for fuel production. I think it's a pity to take all of their straw, to convert it in complicated refineries, and then to burn it. So I would just take the straw, do complicated things, and then get chemicals and materials out of that make use of the structures that I already have from nature that I don't have when I use electrochemical methanol production. But that's my personal vision. That might not necessarily be the vision of the company at the time being.
Okay, so I think this is a really very, very good take-home message from your side, because I totally agree with that, what you said now. And it's super clear that there is good reason to go for that whenever something is already there in a more complex form, to use this and not to do it the other way around. Yeah. So is anyone still there who want to ask something? I don't see a raised hand. So I would suggest now to move forward to the next presentation. So Michael will now give his opinion and his experience in the field. And as we have already heard, it's a presentation that is somehow more or less put in context with that what Michael has told us before. So I'm looking forward to the second presentation. And whenever you have questions, you can already put it into the Q&A session. Okay?
All right. Thank you very much, Gerhard. Actually, your last question was a very nice introduction to what I'm going to talk about. It is the biomass and how we convert biomass into products, and especially into materials and chemicals. So first of all, who are we, or who am I? So I work for Woodcare Plus. Woodcare Plus is a competence center very similar to ASIP. We are focusing on wood chemistry and renewable resources. So Woodcare Plus has been in business for 25 years, around 130 people working here. And we look at wood and renewable resources as materials and technology developers along the entire value chain. So from the field, from the forest, to over the materials, to the end, to dispose any kind of wastes. So we do basic and applied research in close collaboration with industry, and we are active on national and also international projects, a lot of EU funding projects as well. Woodcare Plus is composed of 3 areas. We work on biorefinery processes and composite materials in Linz in Upper Austria. We have renewable material technologies focusing on wood as a building material and other applications in Turin. And we have wood paper and surface technologies in St. Veit in Corinthia. And all this is supported by a strong team for sustainability assessment and impact assessment. So here in Linz, at the biorefinery area, we have 5 teams, and what I'm going to present today are some results of scientific work, mainly from these 3 teams: pulp and fiber, bioprocess technology, and chemical process technology. We are around about 40 people working in these teams, and what you can see also on this slide are some of our key partners in research collaboration projects, industrial, but also scientific partners over the past years. So yes, so lignocellulosic biomass. Why are we working with lignocellulosic biomass? I'm pretty sure most of you know this kind of picture about lignocellulosic biomass. If we look into a plant cell, we will find in the wall of a plant cell these kind of microfibril structures. They give structure to the plant, and they are composed of three major parts. On the one side, you have cellulose, which is basically long polymer of single glucose molecules, and they are in the center of these microfibrils. Cellulose is then covered by layers of hemicellulose, which is composed of other sugars, pentose and hexoses, and also by lignin, which is a complex aromatic molecule composed of these three subunits. So why should we focus on lignocellulosic biomass in biorefineries? So first of all, these refineries are well established. We have timber, paper, agriculture, and so on. There are stable supply chains that can be tapped, as we have heard before. They generate regional value from renewable materials, and in the end, our goal is to reduce the import of critical resources. Giving you some numbers, there is about 2 billion tons of lignocellulosic biomass on Earth. That's a lot. And every year, around 100 billion tons of cellulose is added or is regenerated, let's put it this way. Cellulose is therefore the most abundant biopolymer on Earth. And on second place is either lignin or chitin. It depends who you're talking to, if you're a fan of lignin or chitin, and depending on the calculations in the back. So looking at lignocellulosic biomass refineries and talking about zero waste concepts, I would like to highlight two very successful examples we have in Austria. So there's two companies most of you will be familiar with. It's Lenzing and Austrocell. Both of them are fully integrated, smart biorefineries working basically with a zero waste concept. So let's look at how they do this. In Lenzing, Lenzing dates back to the 1890s with their first endeavors, and they use they use wood chips to produce first of all dissolving wood pulp and fiber-based products as their main product. So lyocell fibers, for example, some of you may know it as Tencel. You have seen this maybe in some stores. But when you produce wood pulp from wood in this biorefinery factory, you will have a lot of side streams. And Lenzing has managed to valorize almost all of these side streams. So you will find acetic acid, for example, which is bio-based and even has a food-grade standard. Fufural is used as a base chemical or drop-in chemical for various processes. They are recovering a lot of salts and other base chemicals from their process to be reused. And from the hemicellulose fraction, xylose is used and turned into, for example, xylitol by other partners. And everything else, which is not being valorized either as a material or a chemical, as we've heard before, can in the end be utilized as a energy source. And in this respect, it's always important to remember that these kind of biorefineries, they are net heat producers. So they produce more heat than they consume. So you can actually use it as a district heating for district heating applications as well. When we look at Austrocell as another example, this looks very similar. So here we have forestry residues, wood chips, but also from other lignocellulosic residues. And again, a complex process of processing these substrates, including chemical recycling and recovery of all side streams. And in this case, it's interesting to highlight that Austrocell was able to establish a bioethanol plant, and since 2022, it's, at least to my knowledge, the biggest operating bioethanol plant in middle of Europe, which is based on wood sugars, so wood-derived substrates. And just recently, last year in 2025, they also announced that they are valorizing their lignin side streams together with the company AgroBioGel to produce products as a soil fertilizer or soil builder. And also this is noteworthy since lignin is often still treated as a side product that cannot be valorized in to sufficient amount. And this is a very nice example how this came into place. So we as WoodK Plus, we like to support these kind of developments as an academic institution. And what I would like to show today are 3 examples of zero waste concepts we have been involved with. So we'll first talk about upcycling spent sulfate liquor from wood biorefineries, then the valorization of waste lyocell granules from Lansing, and also how we managed in a project to close the loop for palm oil residues. So coming to the first example, during this sulfate pulping process, some of you might know that cellulose is separated from wood using some chemicals and high temperature processes where you might get or you will get a side stream which is called spent sulfate liquor. So spent sulfate liquor is nowadays mainly burned for energy recovery, but there is a lot of hemicellulose sugars and lignin inside which can be valorized or upcycled to other processes. The drawback is due to the harsh conditions in the pulping process, you will face a lot of inhibitory compounds in this substrate if you want to use it for microbial processes. So for example, there will be lignosulfonates or different furans formed from the sugar compounds. So to obtain a high value product from this side stream, the SSL had to be first separated into hemicellulose and lignin, and this has been done first by a filtration step and followed by a simulated moving bed chromatography at pilot scale. And in this process, we were able to, or the factory was able to recover 89% of the SSL sugars and also removing most of the inhibitors. So they stayed in the lignin fraction or in the filter cake, and you get a purified lignin fraction that can be used for additive and surfactants. And in this case, we have used the hemicellulose-derived sugar syrup, in short HDSS, to produce lactic acid, a very important base chemical for other processes. How have we done this? We've been using a bacterium called Enterococcus mundi, and with this bacterium, we were able to produce L-lactic acid in a microbial fermentation process from these HDSS sugars. And as you can see here on these pictures or on these graphs, the lactic acid titers were comparable or even higher to pure sugar substrates, and also the growth curve here in solid lines look similar between those two substrates. In a repeated fed batch approach, we were able to show in this work that within 48 hours, you can convert HDSS up to titers of more than 80 grams per liter of lactic acid, and this in repeated cycles, while the biomass is kept constant. And also here you can see that the comparison between glucose and the lignocellulosic sugars is comparable. So with this work that has been actually also performed at pilot scale, it could be indicated that this is feasible also in larger scale. As we thought before, this is always very important to think about it. And we have demonstrated this with an important platform chemical of lactic acid, where yearly about 2 million tons are produced. You could use spent sulfate liquor also for other applications. For example, in another project, we were able to use UV light to detoxify spent sulfate liquor. So if you treat it with UV light, the lignosulfonates will polymerize and face some structural changes. And this higher degree of polymerization can then be used to use a filtration step where the lignosulfonates are separated and the purified sugar fraction in this case has been used with Actinobacillus succinogenes to produce succinic acid. And what was interesting about this fermentation process is that using purified sugar from SSL led to higher succinic acid yields compared to pure sugar concentrations and to less fermentation byproducts. And this is most likely due to the inhibiting of side products like acetic acid, which have been inhibited by the substrate itself, leading to higher succinic acid yields. As a third example for spent sulfate liquor valorization, I would like to show a work performed by my colleague Tom, who used spent sulfate liquor first ultrafiltrated and then using an adsorption step where some of the inhibitory components were removed from the substrate, and the purified or processed spent sulfate liquor has been used for bacterial cellulose formation in Comacatae species. So in this case, we were this specific bacterium is even able to grow on diluted spent sulfate liquor without a pretreatment. And what we have also been showing is that the titer of cellulose from spent sulfate liquor is again higher than in a comparable standard media. And this is most probably due to some aldonic acids that are present in this media and the inhibition of the so-called gluconic acid production pathway in Comacatae, which leads to a higher cellulose formation rates. And in this case, it's especially noteworthy that not only the product itself comes from a green process, but also it outperforms standard media and production processes. And this is always important to implement in these kind of processes, not only to have a green product, but also to have a product with higher performance. And in this case, as already mentioned, we find higher cellulose titers in SSL containing media compared to glucose containing media in two different Comacatae species, but also the cellulose looks different, which is formed. So you will find higher molecular masses and longer fibers and more dense fibers in the cellulose formed from SSL sugars compared to pure sugar bacterial cellulose. And here in the middle is a picture of bacterial cellulose formed from pure sugars where artificial lignosulfonates have been added. So these were three examples how spent sulfate liquor can be utilized in microbial processes. And the second example is about the valorization of waste lyocell granules. So if we go back to the process of lancing, wood pulp is produced or is formed into 10-cell lyocell fibers via this fiber production process, where a specific solvent is used to dissolve the wood pulp and then recovered in a water-based media. This is a very efficient process. Only less than 1% of the cellulose fibers end up in these let's say short chain lyocell granules where the fiber chain length is too short to be used as fibers. And we have been investigating this substrate into more depth. So in the past, it has been simply burned for energy recovery, but in a work performed by a colleague of mine, especially characterization of these lyocell granules has been performed, looking at the molecular weight, the crystallinity, the size distribution of these granules. And then I won't go in too much into detail on this, but more on the second step, how these granules have been enzymatically hydrolyzed to monomeric sugars and then used for a fermentation process. So looking at these granules, they have quite remarkable properties. So they can be very easily saccharified using low enzyme dosages. And you will find here that never dried granules, so the ones which come more or less directly from the process, they have not been dried before, are very easily accessible for enzymes. So you get very high conversion yields compared to, for example, the dissolved wood pulp or Avicel, which is a cellulose-based reference material. So it is a very good substrate for microbial conversion and enzymatic conversion. And this has also been shown here on the right side on this graph, up to a solid load of 20%. We were able to show that enzymatic hydrolysis yields sugar syrups of about 120 grams per liter of glucose with a very constant conversion yield of about 55%. So, or 50 to 60%. So this is very interesting when we talk about integrated biorefineries, that you have such a side stream which is easily converted into new processes, into new products. And again, we have been using this side stream or this substrate to produce L-lactic acid, in this case, with the same microorganism we've been using before. And what we could see here, as expected, basically, since it's a quite pure substrate. So the hydrolyzed granules as a carbon source perform very comparable to pure sugar in terms of lactic acid yields, also on growth. But another aspect which has been tackled in this work is that the solvent that is used in the lyocell process that might be carried over in these lyocell granules can inhibit the microorganisms. So it has been additionally tested to which extent this particular bug, Enterococcus mondei, is able to tolerate the solvent NMMO. And you can see here that even to a load of 100 grams per liter, which is way above what we would see in a microbial process from lyocell granules, you get very stable processes. So 50 grams per liter of NMMO did not lead to any inhibition of the bacterium. So with this work, we were able to show that lyocell granules are actually a very promising cellulosic side stream in terms of purity, crystallinity, but also accessibility for enzymes. And it can be used to generate high sugar concentrations in a microbial feedstock. And it is a very good substrate for microbial conversion to lactic acid or even other products like bioethanol, for example. And in the last example, I would like to show we have been able to close the loop for palm oil residues. Palm oil, as we have already heard, is produced in the million tons range every year, mainly Indonesia and Malaysia here being the largest producers. And if you produce palm oil, so you get the palm fruit, you will end up with a lot of empty fruit bunches where these palm oil fruits or the seeds have been carried with. So for every ton of palm oil in the end, you will end up with 468 kilograms roughly of empty fruit bunches, or short EFB. So this is a high potential lignocellulosic biomass you can use. Palm oil, of course, is on the one side used for food products, but also for biodiesel generation. And if you generate biodiesel, for every ton of biodiesel, you will have 100 grams of crude glycerol in a rough estimation. So what has been performed in the past, especially at Boku in collaboration with the company Vogelbusch, is that they developed a microbial process where this crude glycerol has been turned into valuable chemical compound 1,3-propanediol, widely used in plastics, cosmetics, and other industries. And they found with Lactobacillus deolivorans, they found a very efficient conversion host to produce this base chemical. This process has just one slight drawback. It needs sugar as an additional co-substrate, as LDO-livorans cannot grow on glycerol, and it also needs an additional energy source to convert glycerol to propanediol. So the idea was, why not use the empty fruit bunches, recover the sugar from this lignocellulosic biomass, and feed these sugars into the fermentation process. So here at Woodcare Plus, we do a lot of pre-treatment of biomass, and we have a steam explosion pilot plant we can use. And steam explosion is kind of the widely used as a reference process for microbial, for lignocellulosic biomass treatment. So what you do is you treat this biomass with very high temperatures, up to 220 degrees Celsius, very high pressure for a couple of minutes, and then you suddenly release the pressure and the biomass gets broken up and more accessible for enzymes. The drawback is that with these harsh conditions, you will also form a lot of inhibitory components, like, for example, acetic acid or, again, furfuranls. So one of our company partners, LXP, has an alternative approach to lignocellulosic biomass treatment, and they use concentrated acid in a very high, up to 80% concentrated acid. This acid can be recycled within the process, also a very important aspect. And this enables to use much lower temperatures, so 65 to 85 degrees, and in the end up with lignocellulosic side streams that are purer, cleaner, and more easily separated. So, for example, you can separate the cellulose sugars from the hemicellulose sugars more easily in this process. And to make a long story short, with steam explosion pre-treated empty fruit bunches, it was not able to use the sugars in the fermentation process, but we could show that using empty fruit bunches with LXP-treated biomass, this recovered hydrolysates could be used on the one side to generate biomass. So all the glucose, which is here shown in this graph, comes from the hydrolyzed EFB. Biomass is formed, and after the biomass formation is over, a glycerol feed is added in a fat patch process, and glycerol is turned into 1,3-propanediol and also 3-hydroxypropionic acid as co-products. And this could be facilitated with crude glycerol derived from a biodiesel plant and with hydrolyzed empty fruit bunches after LXP treatment. And what is noteworthy here, so we get similar titers for all three processes. Also, the yields are quite comparable. But what is remarkable is that the productivity of this process or this substrate is comparable on empty fruit bunch hydrolysates to pure sugars or pure glucose, which has not been shown before for other wood hydrolysates or other alternative sugar sources. So with this process or with this project, it has been shown that 1,3-propanediol can be produced entirely from oil-based, palm oil-based residues. And this process has even been scaled up to a 100-liter scale. So also here, when we are talking about scaling, this has been proven. So yeah, with these three examples on how to convert lignocellulosic side streams into value-added compounds, I would like to finish my presentation for today. And as we've heard before, it is very important for us to use all our natural resources in increasing the resilience of European economies, especially in times like these. I think for everyone here, it's clear every waste stream is a potential source for a new product. So I don't like to call them waste streams. I like to call them side streams. And what we need, as also the previous speaker has been saying, we need smart and integrated refineries or biorefineries to make these processes economically viable. With this, I'd like to thank my two co-workers who have been delivering slides for this presentation today, and also you for your attention. And if you have any kind of side stream you would like to utilize, don't hesitate to contact us. Thank you very much.
Okay, thank you, Michael, for this very, very interesting presentation. And I think we are open for discussion. Is there any question from the audience?
There is a question in the question and answer section.
Okay.
Also from Antonia Zerobin. Can you share with me an approximate number of how much agricultural residues are not yet utilized in Austria? And are the farmers aware of this high potential?
Yeah, as we've heard before, there is no straw in Austria. So most of the straw, let's say all of the straw, is somehow utilized. So if you think, for example, of wheat straw, it can be used for cattle farming. I don't know the English word now, like for Einstreu in a farm. And so there is some utilization already. Approximate numbers, it's difficult because depends very much on what kind of agricultural residue. But the way I like to approach this is to generate a scenario where we can actually add value. So, for example, in a project, we have been investigating whether we can extract from wheat straw certain compounds, high value, high molecular weight compounds that can be used, for example, in cosmetics, and then the residual biomass still be used for agricultural purposes. Yeah? So adding value to established business concepts is, in my opinion, the way to go here.
Okay. So then I will continue with one question related to this use of spent sulfide liquor. You showed us the results from fermentation, and you end up with higher yields and lower byproduct formation compared to conventional glucose as the carbon source. Is it surprising, or is it something that you would have expected before you started?
Well, in this case, it was not too surprising because we are dealing with a very complex substrate, so to say. So there is not only sugars in there. There is some organic acids in there that can serve as an additional carbon source. So this is, of course, one aspect. It has been compared to traditional sugar fermentations. So these potential additional carbon sources like organic acids, they add up, of course, to the yield. On the other side, what was a bit surprising, or what has been reported in literature, but not very much into detail, is that some of the compounds in this spent sulfate liquor can inhibit side pathways, or let's call them undesired pathways. In, for example, succinic acid production. So you're inhibiting co-formation of acetic acid and redirecting carbon into the succinic acid production. So this has been shown, and there is actually also some work going on to characterize this in more detail.
So this could then be used, for instance, to set up a new type of media for conventional processes. So
yes,
to
exactly.
learn from that what you have experienced in your work.
That might be an option, yes.
Then there is a very general question. Whenever you go for this type of processes, I think that the techno-economical assessment is always included, and it's always part of your work. So, and you also said you don't want to say waste, but it's side streams. Yeah.
Yes.
So how can you somehow consider or build up scenarios where you can get a good assessment what may happen with the material that you use as the carbon source, for instance? Whenever you have a process that is working in a certain way, the price for this side stream will be higher, or? Because other people can also use the technology and can make use of the side stream in a better way, so the price level will increase. For instance, the glycerol.
I'm not entirely sure if I get the question right. So when we look at established biorefineries, like for example Lenzing, any side product that is not utilized in terms of materials, chemicals, and so on, in the end goes into their wastewater or biogas treatment plant. So they are generating already some value, may it be heat or electricity. So what we are trying is to find a way or find a conversion process that is generating even more value. So that is, of course, the task. If you supplement an existing process, it needs to have an economic benefit for the company. This is for sure.
And you also provided this number. There is 1% of these granules that you use as a side stream. And it is also very clear that the scales that you're talking about are somehow different to that what we are used to in conventional biotech. Yeah. How can you, or how do you more or less consider this problem or the the issues to be expected if you then do the scale up when you do the development of this type of processes? Because development is still at a very more or less small scale, or?
Yes, of course. So on the one side, we try to use real substrates as soon as possible. So when we develop processes, we want to work with the real substrate. So may it be spent sulfate liquor or whatsoever. So this the earliest possible we really go to these substrates. And when it comes to scale up, so we at Wood Plus, we have the ability to go up to fermentation capacities of 30 liters. So that's the scale we can show or we can prove. Anything beyond we do with partners. But when we design a process, may it be media composition, may it be the fermentation strategy, we always try to keep it as simple as possible. So, for example, if it is possible to use an alternative nitrogen source, for example, a waste stream nitrogen source, we would try to incorporate this from the beginning, or when it comes to media. Or if we think of bioprocess development, also here, always try to have a process that is as simple as possible, I would call it, in to make it easier to scale it up in terms of economy, because what we always need to consider, the products we are producing in the end are somewhere between, I would say, 1 to 10 euros per kilogram, whether products for cosmetics or pharma, of course, are much, much higher. So we cannot afford tedious and complicated purification processes like, I don't know, multi-step chromatography will never be feasible for these kind of processes. So we need to keep it as simple as possible and use other equipments. Let's put it like this.
Yeah, but this is maybe also good news for process engineering, because it's much more focused on a good process, because the process is so very closely connected to the costs, which is maybe no longer the case if we talk about biopharma product. Okay,
yes.
Is there any other question from the audience? Is there anything in the Q&A? If not, I think we can